Hello everyone, myself I'm Tahira Mazumder and I'm basically a faculty in IT department in AKGEC Engineering College. Today I'll be talking on the topic of on this topic which comes under the subject of computer networks, and the topic is UDP versus TCP, which are protocols that comes under transport layer. So transport layer, as we all know, it is one of the layer in OSI model. So we'll be talking in depth about TCP and UDP and the difference between these two. And before that, I'll just talk about a little bit in detail about what is transport layer, what are the features or what are the things that happens in transport layer, and then we'll move on to UDP and TCP. To start with, let us first briefly talk about what is transport layer. Transport layer basically is a layer which deals with process-to-process delivery, and the transport layer, it is responsible for the transmission of packets. Basically, when you're in the transport layer, we don't call them as packets, we call them as segments, and it deals with the transmission of segments from process to process. When you're saying from process to process, the one process is a process that starts from the sender's end, and the other one is a process that is at the receiver's end. And so this layer basically deals with the delivery of packets which are part of messages from one process to another. We'll be talking about more of these topics later on as we proceed. We'll be talking about non-server paradigm, multiplexing, demultiplexing, the difference between connectionless, connection-oriented services, what is the difference between reliable and unreliability, and some more protocols. So why do we need transport layer? What is the need of transport layer? The transport layer is basically needed for ensuring that the packets that starts from the sender system, it is reaching safely and without any errors at the receiver system. So transport layer basically it is executed at the user system. That is what we need to remember. By user, we are talking about the sender system and the receiver system. And if you compare this transport layer with the network layer basically runs on routers, while transport layer runs on the computer system at the user's end, that is at the receivers and the sender's end. And normally the packets that are lost are usually managed, detected, and somehow handled by this particular layer, which you call them as the transport layer. So this is a figurative representation of how exactly things work out. So when you're talking about transport layer, we are talking about a layer that is dealing with process-to-process transmission. When you're saying process, that means the processes that are there at the sender's end, and that is and the other one that is there at the receiver's end. This is what the transport layer deals with. Now, if you compare this with the network layer is basically, we call it as host-to-host system, which deals with host-to-host delivery. And we can say that the data link layer is basically node-to-node delivery. So transport layer is going a little bit in the higher level where it deals with process-to-process delivery. So when you're talking about transport layer, there are some terminologies which are important and which needs to be noted. One of the important terminologies is port number. What is port number? Now, port number basically, it is a way to identify a specific process. When you're saying process, the process can be at the receiver's end or at the sender's end, to identify a specific process to which an internet or other network message is to be forwarded when it is arriving at a server. So all network connected devices basically have processes via which packets are being transmitted from the sender and the receiver. And to identify the process, we have ports. So ports are used to basically relate to the process from which it is being starting, from which the transmission starts at the sender's end and it is received at the receiver's end. So we have this data and client. Let us say this is an example of a process with port number 552.52000. Let us say at the server's end, we have another process where the port number is 13, and so we have a transmission between two processes with two port numbers 52000 and 13. So when you are transmitting the segments or transmitting the data from the sender's end to the receiver's end, we have the data part. In addition to the data part, we also say where from is the data coming and where it is going. In case of this is let us say this is the source. That means, from the sender's end, when the data is being transmitted from the sender to the receiver, what is the first field? The first field indicates the port number of the sender. The second field indicates the port number of the receiver, and followed by the data. The sender is also called as the source and the receiver, the sender is also called as the source, and the receiver is also called as the destination. And obviously when we have packets or segments flowing from the server's end to the client's end, the numbering is reversed, right? Because here the destination obviously is, when you're going at the other end, the destination is 52000 and the source is 13. So port numbers are basically numbers via which we identify the processes which are involved in the communication between the two ends. So if you compare IP addresses with port numbers, if you remember what are IP addresses? IP addresses basically are addresses that are used, or that are addresses that come into the picture when we are talking about the network layer. So when you're comparing IP address which is being talked about in network layer, we have talked about IP addresses when we are dealing with network layer, and when we are dealing with port numbers, we are basically talking about transport layer. So IP addresses which are talked about or which are dealt with in network layer versus port numbers that are there in transport layer. So if you compare these two, we are saying that we have this, you have the IP packet, which is prefixed by the IP header. The IP header, in this case, we are saying it is an IP address. IP address, we all know it can be either in IPv4 or IPv6 format. In addition to that, we have now from the network layer, the data is being transmitted, let us say, to the transport layer. Now it is prefixed by the transport layer header and the data that is coming from, that is related to the transport layer. Now in the transport layer, this is the part related to IP address, which is dealing with network layer, and this is the part related to the port addresses, which deals with the port numbers of the sender and the receiver. So we have the summarization is that when we are moving from transport layer to the network layer, the port numbers are being further appended with the IP addresses. So it is something like this. You have port numbers to identify the process inside a system, and you have IP addresses to identify a system. Out of the many multiple systems that are connected over the internet, we have IP addresses to identify a certain computer system. And once a computer system is identified, next, which process to which the connection is to be established, it is identified using the port number. So this is the basic difference between IP address and port number. Now, what we are basically doing right now is that we are taking up some terminologies which are very much relevant when you're talking about transport layer. So the next term that we'll be talking about is IANA. What is IANA? The full form of IANA is Internet Assigned Number Authority. Internet Assigned Number Authority. And this particular, basically through IANA, we are dividing the port numbers into 3 ranges, and those ranges are named as well-known, registered, or dynamic. So we have the port numbers which goes from 0 to 65536 bits, for example, and out of this we have well-known ports where from 0 to 1023 are reserved by well-known names, which are assigned and controlled by the authority, which we call it as IANA, which stands for Internet Assigned Number Authority. And these are well-known ports in the sense that these ports are known globally and all are aware of the port number and the corresponding meaning or corresponding process to which that port number relates to. Now we have another kind of port number which we are calling them as registered ports. Registered ports starts from the number 1024 and starts from port number 1024 and ends with port number 49151. What are registered port numbers? These port numbers, they are not assigned or controlled by ANA. That means they are beyond the control of ANA, and they can only be registered with the ANA to universally having any unique names. Now we have the next one that is called the dynamic port. The dynamic port ranges from 49152 to 6553 port numbers, and these port numbers, they are neither controlled nor registered. They can only be used by any processes, and we also call these port numbers as ephemeral ports. These port numbers are also called as ephemeral ports. So these are the 3 categories of port numbers, or rather we can say out of the total range of port numbers are divided into 3 categories. The first one is well-known ports, which is directly controlled by the INA. Other than that, we have registered ports and dynamic ports, which are also called as ephemeral ports. Now, let us take another terminology which you call them as socket address. What exactly do you mean by socket addresses? So we know that when there is any network data transmission in through computer networking, so when we need to identify the system to which the transmission is to be done, and one that is done via the IP address. And once the system is identified, then we need to identify the processes between which the communication is to be established, and that is done through the port number, as I told previously. Now, the combination of the IP address and the port number. The IP address, that means the system to which the connection is being established, and the port number, that means the process within the system via which the connection is to be established. This two combination makes up the socket address. These are some terms which will be used frequently in the layer when you're talking about transport layer, and they are very much more important significances. So they are used basically the port number because it is basically dealing with the IP address. In addition to the port number, that it is used for realizing the end-to-end connection, and this combination between these two, we call it as the socket number. So we can say basically whenever we need a data transmission for any data transmission, we have the source and the destination between which the transmission is to be done. So obviously we need to have two pairs of socket number. We need to have two pairs of socket addresses or socket number. That one is at the client side, from which the request will be generated for establishment of the connection, and the other one is at the server side. So you have two pairs, one at the client and the servers, and the other one will be the server side. And these four pieces of information, they are part of the IP header and the transport layer protocol header. So the two pairs, that means the socket number of the source and the destination, they are very much an important integrity of the IP header and the transport layer protocol header. The IP header, we can say then it contains the IP address. The UDP ITP header contains the port number. So when you're talking about the UDP IT header, we are basically talking about dealing with port addresses, and when you're talking about the IP header, we talk about the IP addresses. And so when you are establishing a communication between the source and the destination, we need to have a pair of socket addresses for the source and the destination. So we have another concept that is called as multiplexing and demultiplexing. In this case, what we are doing is that, let us say this is at the source or the sender's end, and this is at the destination or the receiver's end. Now, when we are talking about at the sender's end, source, or we call also this as the sender's end, and this is the destination, and it is also called as the receiver's end. Right. Now, when we are talking about communication between the source and the sender, let us say the sender's end. In the sender's computer system, we don't have one process, but we have multiple processes in a computer system. So whenever we are to establish a communication between two systems, so we need to have an IP address. Obviously, this IP address is used for basically identifying the computer. The IP address is used to identifying the system that is connected in the internet. And out of the multiple processes, only one process will be selected, which will be communicating through the IP address and via the network to the destination. So basically, multiplexer, we all know multiplexer. When you're talking about multiplexer is a device, we can say, which is a many to one communication. So since we have multiple processes, where out of the multiple processes, only one process will be connecting. So out of this many processes, only one process will be sending a packet. So we have many to one communication at the sender's end. So we have multiplexer concept implemented at the sender's end. Similarly, at the receiver's end, it is different. We have one which can go to any one of the processes. So we have one-to-many, which is realized by demultiplexer, one-to-many communication, which is realized by demultiplexer. And so at the receiver's end, we require demultiplexing. So basically, the transport layer, we can say it receives datagram from the network layer after the error checking and dropping of the networks. The transport layer, they basically deliver the messages to the appropriate processes based on the address or based on the port number, which it identifies from the header, that is being from the header. By header, we are talking about the header at the transport layer, which gives the corresponding port number. So we have this concept of multiplexing at the sender's end, where out of the multiple processes, only one process will be selected via which the data transmission will be done. And we have demultiplexing at the receiver's end, where out of the one input that has been coming will be diverted to any one of the processes that are there in the system. So we have multiplexer at the sender's end and demultiplexed at the receiver's end. Now coming to the topic of protocols. When you're talking about the protocols in transport layer, so we have basically our next topic of discussion are the protocols. We know what are protocols. Protocols, basically by protocols we are talking about a set of rules that needs to be followed. So when you're talking about protocols in transport layer, we have three important protocols that are there in transport layer. We call them as namely UDP, TCP and SCTP. User Datagram Protocol transfer. We have UDP, TCP and SCP in TCP episode, and this is where these protocols are there. So today we'll be basically, if you look at the placement, we have the OSI model, the layers in OSI model. We have at the beginning, at the lowest end with the physical layer, followed by data link layer, followed by network layer. This is some of the protocols that are there in network layer, like namely ARP, IP, ICMP, and so on. And then when you're going to transport layer, this is some of the important protocols. Today we'll be talking about TCP and UDP in detail. And followed by, when you're going to the transmission application layer, this is some of the protocols. So this is where the transport layer protocols are being placed when you see the entire structure of TCP IP suite. So today we'll be talking about TCP and UDP. So let us start with UDP. The full form of UDP is User Datagram Protocols. UDP's full form is User Datagram Protocol. So basically we can say UDP protocol, it is also called as connectionless and it is unreliable transport protocol. What do you mean by connectionless? By connectionless, we are saying the connection for any data transmission, a secured connection need not be established on as and when the connection needs to be required. The connection will be established between the two systems, and the packets between the sender or between the source and the destination, they need not follow a fixed pattern. They can follow a pattern as and when the availability is there for the path. So it doesn't add. When you're talking about UDP, it is basically a very simple protocol which has very less complexity. If you're comparing it to TCP, TCP is much more complex than UDP. So to start with, we'll just first discuss about UDP and then we'll move on to TCP. So TCP is very basic. It does not add anything to the services which are already existing in the IP layer, except that it has this feature of adding up more details about the process-to-process communication. What do you mean by adding up more details? We're talking about adding up the process numbers, or rather the port numbers involved at the source and at the destination. And this is the only thing add-on which the UDP does. Other than that, it doesn't have that much more functionality if you compare it with the TCP protocol. So we can say these are some of the features that are very significant in UDP. It is connectionless service. That means when you're talking about connectionless, we are not securing the communication. We are not ensuring that a fixed path is being followed by all the packets that needs to be transmitted. Each packets in the transmission are independent, or each datagram that is to be sent by the UDP, they follow their own independent routes or their independent datagrams, and a fixed route need not be established. This is very much unlike TCP. And the feature, we are talking about flow control and error control. UDP, as I said, it is very simple, very, very simplistic protocol. It is simple, unreliable transport protocol. And there is no flow control, no concept of flow control, and hence there is no concept of window mechanism. So in this case, we may have the problem of the receiver getting overflowed with incoming number of, with an increasing number of messages, because we don't have the features of flow control. Now, another feature which is very significant in UDP is queuing. Here we have queues that are associated with ports. We have, when you're talking about ports, we have two ports. One is the port at the sender's end or at the source end, and the other one is the port at the receiver's end. So, so in this case, the queue, we have two queues, and those are, if you are talking about client-server architecture, then the queues are maintained one at the client side and the other one is maintained at the server side. Now, one very important point that needs to be remembered is that when we have two ends, the client and the server, if you're talking about client-server communication, then when you have these 2 points, normally when you're talking about queues that are associated with client side, the port numbers that are used at the client sides are normally ephemeral. That means when we are talking about ports that are dealing with clients, the port numbers are ephemeral numbers. And when you're talking about ports that are at the server's side, here the port numbers that are used at the server side, they are well-known ports. Where servers are using well-known ports, while clients use ephemeral ports. So this is a point which needs to be remembered, and we will be taking up this as we proceed. We'll taking up a numerical to understand the concept more about this. And one more point that needs to be understood is that these queues will be remaining open as long as the server is running. So the queues will continue to exist till such time there is a communication between the client server. Once the communication ceases, then the queues will cease to exist. So this is the example. If you say, so we have the queues at the server's end and at the client's end. So you have two sets of queues. One is meant for the outgoing purpose and the other one is meant for the incoming purpose. Same at the server side. Now, if you see the port number, at the client side, the port number is 52000, and at the server side, the port number is 13. So if you look at it, what is 52000 and what is 13? In which range of the port number do they exist? If you just brush up, you can see that initially when I have told, when you're talking about 13 is a number that lies between 0 to 1023. That means 13 is a port number which comes under the category of well-known ports. And what is the other port number? The other port number was 52000. We had two port numbers in that example. One was 13 and the other one was 52000. So 13 is, if you see, it is within the range of 0 to 1024. So 13 is well-known port. And the other one was 52000. 52000 is coming within the range of ephemeral port. So 52000 is coming under the category of ephemeral port. Under the category of ephemeral port. So we have, if you see, so 13 is a well-known port and 52000 is ephemeral port number. So let us go back to where we were. We are here. So if you see, 13 is a well-known port number. It is a well-known port number. And if you see, as I told you in the previous slide, that server's side, they have port numbers which are well-known ports, and client's side, at the client side, we have port numbers which are ephemerals, and at the server side we have port numbers which are well known. That means if you just look at it, the client is having a port number which is ephemeral. Fine. And we can say the server is having a port number which is well known. So we can say if you have any port numbers and if you want to identify whether it is a client or a server, you just look at the port number, see whether the port number comes under the well-known range. If it comes under the well-known port number ranges, then we can say yes, this is basically a server side. And if it does not come under the well-known port range, then we'll say this particular process is basically a client process. Now, this are some examples of port numbers. If you just look at these port numbers, these are numbers from range 0 to 1023. This port number 1 is 7, 9, 11. All of this comes under this range. So all these port numbers are basically under the category of well-known port numbers. So we can say and if you just take up, so all these port numbers are well known and they have pre-designated meaning also. So we can say, let us say port number 7. What does this mean? It means echo. What is echo? What is the meaning of echo? Echo basically receives a datagram back to it basically echoes a received datagram back to the server, or back to the sender. So we have these, let us take one more example. Let us say port number 13. What is port number 13? It means the protocol data time, and what it does, it basically returns the date and the time. Let us take another example. Let us say we have port number 17. And what is port number 17? It stands for code protocol. And what does this protocol do? It returns a code of the day. And similarly, you have 10 to 1023. So you've got this much number of protocols, which are pre-designated with pre-designated meaning given to them, and we'll be using these port numbers are used at the server's end. This is a point which we need to keep that in mind. So these are more things about UDP. This if you just take a simple example, let us say if you're taking a simple example of a UDP format. So we can say a UDP is having a format a simple UDP packet, when you're talking about packets that starts flowing from the process at the source to the process at the destination, we are talking about the packets that follows UDP protocol. Then each of the packet that is being transmitted from the sender to the receiver, each of the packet will need to have this particular format. And what is the format? Each packet or each user datagram will be having two, we normally call them, rather basically we don't call them as packets, we normally call them as segments when you're dealing with transport layer, or we also call each of the unit, transmitting unit, as datagrams. So each of the data, we can say each of the datagrams, so each of the segments at the transport layer has two important fields. One is the header, which gives, but the very name says, one is the header, which basically gives a description about the data that is being stored in that particular segment or in that particular datagram, and which also describes more about the port numbers, the source and the destination port numbers, the entire details about that particular segment that will be transmitted from the source to the destination is given. The details is given in the header, and the data that is being transmitted will be given in the following field, that is the data. So the data is something which is variable, which is variable, and it will vary from time to time based on the data that is being transmitted between the sender and the receiver. But when you're talking about the header needs to have a fixed format, and the format of the header in this case is 8 bytes. When you're talking about UDP format, every header of the UDP format is made up of 8 bytes. And when you're talking about 8 bytes, we basically are talking about 64 bits. We are saying the header of a UDP format basically is having 64 bits. And this is how the 64-bit is. Like we have 16 bits, which is reserved for the source port number. We have 16-bit for the destination port number. We have 16-bit reserved for the total length. We have 16-bit reserved for the checksum. So the whole thing totals and adds up to 64 bits. So the header first it gives the port number of the source, then the port number of the destination, then the total length, and finally the fourth 16-bit that is used for checksum. So to understand more about this concept, so let us just take an example. This is a dump of a UDP header in a hexadecimal format. Let us say this is the dump of a UDP format, and let us identify the meaning. From this format, let us see what is the source port number, what is the destination, what is the total length, and so on. This is how the question is that needs to be answered with this particular data that is been given. So let us say this is the dump of a UDP header. This is a UDP header. If you remember, the UDP header is of 64-bit, or we can also say as 8-bit. And this 64-bit will be organized as the first 16-bit needs to source port number, the next 16-bit as the destination port number, followed by 16-bit for the total length and 16-bit for the checksum. So if you look at it, this is how from this particular example, we take up this is something in hexadecimal format. This is in hexadecimal format. So we have this what is the source port number? So first 16-bit will be given by the first 4-digit hexadecimal digit. So what we take up the first 16-bit, first 4 digits. It is 0632. This is in hexa. Now if you convert it in decimal, it is 1586. It is in decimal. So the port number, the source port number is 1536. We can convert it into hexa, and then we can see that the value is 1586. Now when you're converting into hexa, we can see, we all know the conversion. How is the conversion? The conversion is, if you want to convert into 632 into hexa form, so we have 6 into 16 to the power 2 plus 3 into 16 to the power 1 plus 2 into 16 to the power 0. And if you do the calculation, you'll find that this is equal to 1586 in decimal form. So this port number, the source port number basically is 1568. We can say it is in decimal, and in hexa it is 032. And let us move on to the, give me a moment. Okay, now let us move on to the port number of the destination. The destination port number is the following next 4-digit number. The next 4-digit number is 000D. 000D is 00 is all, we know the meaning of hexa. 0 is same as decimal 0. D is 13 if you remember. in case of decimal number. So the destination port number is 13. We can say if you're taking it the decimal form, or you can say it is D if you're taking the hexa form. And next question is what is the total length of the user datagram? The total length of the user datagram, if you look at this example, it will be what is the user datagram total length is 16-bit. The total length is 16-bit. So the next 16-bit, that is E217. So the total length it is E217 in hexa form. This is the total length. And if you convert it in decimal form, like the way I have explained here, it is basically equal to 28 in decimal. Fine. So the total length of the user datagram is this. And out of the total length, what is the length of the data? If you see, the 8 bytes are reserved for the header. So the length of the data will be 28 minus 20, which is 20 bytes. So the length of the data is of 20 bytes. And next question is, what is the packet? Whether using this particular dump, how will you make out what is the packet? Whether it is flowing from a client or to a server, which one it is. So if you look at the datagram number, and if you see that the source number and the destination number, you are seeing that the destination number is 13. Destination 13 means destination 13 is a well-known port. So it is going to, the destination is 13. That means it is going to a well-known port, and a well-known port only servers have. So it is going to a server. That means this is starting from a process, from a client process. Hence, we are saying it is going from a client to a server. Why? Because the destination number is 13. The destination number is 13, which is a server, because only servers have well-known ports, and hence it is going from a 13. And what is the client process? If you see, if I have told you here, 13 basically is a daytime process. So 13 basically, the client process is a daytime process. So this is an example of a dump of a UDP header. Now, when you are talking about TCP, TCP basically is connection oriented. That means connection is established before the data communication. A fixed connection is established, and once the connection is established, the same connection is used by all the datagrams that needs to be transmitted from the source to the destination. So it creates a virtual connection, as I told you. Of course, the connection is not physical connection; it's a virtual connection that lasts only for that particular session. And in addition, TCP also has flow and error control. So this is an example. This is a virtual connection that is first established. And then once the connection is established, data flow is established between the sender to the receiver is established. So TCP, we can say it is a stream-oriented protocol, because you have a stream of bytes that are flowing in one direction till such time the entire session expires, and that stream of that channel will be followed throughout the transmission, or till the datagram, till all the datagrams are being transmitted. And this is something which is virtual. That means it is not a physical entity. We establish the connection only for that session. The connection is over, the session expires. So we say there's an imaginary queue. And every TCP segments basically have this two, we can say, TCP segments. They are basically the IP layer, we can say it is a service provider for TCP. And we have TCP, we have buffers. Okay. Now, let us come to the TCP segment format. We are talking about TCP. TCP, if you compare with TCP with UDP, TCP is connection oriented, while UDP is connectionless. TCP takes care of flow control and error control, while UDP does not take care. And this is the pattern of TCP format. You have the header followed by the data. Here the header in case of TCP is quite high, a little bigger in size. 16-bit for port number, 16-bit for destination ports, 32-bit for sequence number, 32 for acknowledgement number, followed by H length, followed by reserved bits, followed by window size for 16-bit, checksum 16-bit, urgent pointers which will be having 16-bit, and then subsequently we do some bit of padding to add up to the number of 16 bits. So this is the typical format of a TCP header. And the flags that are, if you see the flags that are there in the TCP header format, where these are some of the flags, URG, AC, this is all the flags. And the meaning of these flags, let us say URG is basically its meaning talking about urgent pointers. AC, K, it is relating to the value of the acknowledgement field, saying that it is a valid field. PSH stands for pushing the data, and so on. These are the flags, the meaning of the flags that were there in the file in the format of a TCP header. Now, if you just take up a dump of a TCP, if I compare this a dump of a TCP header with that of a UDP header, let us say this is the dump of a TCP header. As I told you, a TCP header format is much more bigger compared to UDP. Why so? Because TCP has much more complexity, because it is taking care of establishing the connections, taking care of handling the flows and error controls. So, if you look at it, if you remember, this is the header format. So what is the source port number? So we just have to trace up the first 16 bit, that will be the source port number. The next 16 bit will give you the destination port number. What is the sequence number? The sequence number will be followed by the next 32 bit. What is the acknowledgement number? The following next 32 bit, the following 32 bit will give the acknowledgement number. The length of the header, if you look at it, the length of the header will be given by the next 16 bit. And what is it? We'll take up this numerical and let us take up this numerical in detail. So if you look at it, this is an example of a TCP, of a dump of a TCP header. This is the source. What is the source port number? The source port number is the first 16 bits. So right now we are talking about, this is the 4 into 4, 16. So every one digit of in hexa represents 4 bit. So we have 4 digits representing 16 bit. The first 4 digit basically is the source number, and it is basically 1330 in decimal. The next 4 digit, that is 000167, it is the destination port number. The sequence number is the next 32 bit. The next 32 bit is, if you just see, it is the next 32 bit is all zeros followed by 1. So this is your sequence number. The next 32 bit is the acknowledgement number. It is all zeros. The acknowledgement number is all 0. The header length, if you see, what is the header length? The header length is the next 4 bit. The next 4 bit is 5 here. So the header length is 5 in hexa. It is 5. 5 in hexa. So now if you normally it is, we are talking about, we will multiply it by 4 to get the total size, which equals to 20 bytes. The control bit, fill bit is 0. It is basically 002, because if you just see, the control bit is, it is requiring 3 bits. So the control bits is taking up those 3 digits. And this 002 basically relates to sync. Sync is having the control bit pattern 002. So the control bit is 002. Next is, what is the window size? The window size is the next pattern, the next 16 bit. The next 16 bit is 07FF. So 07FF is the window size. In decimal, it is 2047. So this is the window size. And followed by, if you want the other bits, if you want to know the other things, the remaining fields, if they are data, it will relate to this. And if it doesn't have, then you're going for some padding and so on. So this is the file format of a TCP dump. So if you compare, we can say that TCP is much more complex than UDP, but it takes care of lots of functionalities. So we can say TCP is connection oriented, UDP is not connection oriented. TCP is highly reliable because it has lots of more functionalities, unlike UDP. UDP is not reliable. So because TCP takes care of so many components, so TCP obviously will turn out to be slower. So you'll be taking for UDP, will be going for UDP when you're not going for, when the requirements are not very strict. In that case, you'll go for UDP communication. That, as I have seen, the UDP size of, the header size of UDP is 8 byte, while that of TCP is almost double of that. So TCP has got a much bigger header size. And both of them, TCP and UDP, they check for errors, but only TCP can correct the errors, since it has the techniques to handle flow and flow control and error control. These are some of the applications. TCP is it helps to establish communication between different types of computers, and it supports many routing protocols. It also enables internet working, and it can be operated independently. These are some of the examples, applications of UDP. Okay, that much for now. So I'll be talking more on this particular subject, computer networks. Maybe I'll come up with some more topic in the next class or next lecture that I'll be taking up. That much for now. I'm winding up.